And remember that you have, I forget which homework off the top of my head. So on Monday night this week, you have quite a bit due this week. You have 6.2, 6.3, and 6.4 due on Monday night. Right? So don't get behind now. So let's talk about this. I wanted to point this one out because this uses a second type of bearing. The bearing that we saw first looks something like this. You would do that or that, something like that. You would first go south or go north, and then from there you would either go east or west. So that's the first type of bearing. And the second type of bearing is from the North Pole clockwise. So that's also different than the standard way we think about angles in general. In general, we think about angles rotating counterclockwise from the positive x-axis. That's how we think about angles in general. But when we're talking about navigation, there are two types of bearing. When we're talking about the application, whether it's an aerial navigation problem or a boat navigation problem, we use one of these two types of bearings. So the only time we don't rotate counterclockwise from the positive x is if we're dealing with a navigation type of problem. And it will be obvious when we're dealing with one of those problems. So typically you'll see this type of bearing, south, north, and then east or west from there. With boat navigation, typically you'll see this type of navigation where we go from the North Pole clockwise with aerial navigation. So this says that an airplane leaves an airport and travels 100 miles in a direction of 300 degrees. So if you're dealing with an application and you're dealing with navigation and they just say that, you should be thinking, okay, it's a navigation application, so I'm rotating from the positive, from the North Pole, the positive y-axis clockwise. So, up in with typical problems, if I say 300 degrees, you should actually be thinking that. Counterclockwise rotation from the positive x down into quadrant 4, there's 270, there's 300. That's what you should be thinking of if I just say, hey, 300-degree angle, where is it? You should say quadrant 4. But if the context is application, navigation, then we're going to rotate from the positive, from the North Pole, in the clockwise direction, not the counterclockwise direction. So a little bit of ambiguity there. Not consistent, unfortunately. Okay. So we're leaving the airport at 300 degrees, and we fly 100 miles. So 300 degrees means that we're 30 degrees past the negative x-axis. How far north of the airport is the plane then? So what I've done is pulled out this reference triangle here. So that's right over here. And it's saying how far north of the airport is the plane. Well, if that's 100 miles, this side of the triangle is going to represent how far north we are. And this side of the triangle is going to represent how far west we are from the airport. The airport would be right over here. So we need those two dimensions of the triangle. And we're told that the angle is 300. Again, that takes us 30 past 270. 270 because it's 90 plus 90 plus 90. It's 270 and 30 more. So that would be the angle in this triangle, in this reference triangle. So we have a few ways to do this. We could go all the way back to looking at our 30, 60, 90 triangle and saying, oh, the typical side lengths that we chose back then, the easiest ones were 1, 2, root 3. We could go back to that, totally fine. Or we could go to the unit circle and say, oh, we know the coordinates of this point on the unit circle. So this point right here is corresponding to this, except that I'm on a unit circle, not a circle of radius 100. And on the unit circle, those coordinates are going to be, if I take this, you can see this triangle here, that's going to fit in here perfectly if I force that hypotenuse to be what value? Right now the value is 2, so it's too big. What would I have to do to all three sides to force it to fit right inside a unit circle? Yeah, divide by 2. So if we divide all 3 sides of this by 2, then we'll actually be on the unit circle, and this would be, the x-coordinate would be negative 3, root 3 over 2. The y-coordinate would be positive 1/2. So if we decided to use a unit circle, so we have several different ways we can think about this. Because what we need to figure out n and w, we need to know the trig function values of 30. Right? So if we want to solve for n and we look at this triangle, we're going to say sine of 30 is n divided by 100. So n is 100 sine 30. And to get that value, sine 30, we either look at this, we can look at this triangle in red. Let me take off the green here just so that we can see that there's distinctly 2 different ways we can go to get the same answer. We could say sine of 30 looking here. Oh yeah, our representative, 30, 60, 90, it's opposite over hypotenuse, so that's 1 over 2, that's 1/2. Absolutely fine. We could also say, hey, let's go to a unit circle, and the point on the unit circle right there, we will have the cosine value being negative root 3 over 2 and the sine value being 1/2 if the hypotenuse is 1. So that also works. Regardless, we get 100 times 1/2. And that will be 50, and our units are miles, I believe. I'll assume miles for now. If I'm wrong, I'm sure you'll tell me. So, and that's north. Let's make sure that that's clear. So this is north of the airport. And then west of the airport's this other dimension. So west of the airport, we would use the cosine of 30 degrees. That's going to be w over 100. So we'll have w equals 100 times cosine of 30. And cosine of 30 is root 3 over 2. So that's going to be 50. I did say one thing I want to actually clarify. So that's 50 root 3 miles if we leave it in exact form. 50 root 3 miles. If my math lab says approximate to the nearest 10th, you go to your calculator, you type 50 square root 3, and you approximate to the nearest 10th, if that's what it asks. If it says leave it exact, leave it exact. So I want to point out one thing. This down here, in both of these, are asking for sine of 30. I actually drew this angle over here looking like the plane was looking, but really, if we're looking at 30 degrees, we're focusing on quadrant 1 over here, and the way we constructed the problem, we were actually asking the question, what is sine and cosine of 30 degrees? So it's actually this point over here where we have cosine right there of 30 and sine of 30 right there. So those are the 2 values that we would want to use if we were going to use the angle of 30 degrees. Right there. So over here at 150 degrees, they have the same sine value, but really we should be looking at 30 degrees, not 150, if we're focusing on this triangle that has an angle of 30. All right, any questions on how we generate those values? And that's west. Is there clarity on what we mean by exact and approximate? Is it clear that 50 root 3 is the exact answer? And as soon as you type it in the calculator, you're approximating. Square root of 3 as a decimal is an approximation. As soon as you write down any decimal form of root 3, it's an approximation because that decimal expansion goes on forever. So as soon as you stop writing, you've approximated. Because the exact value would go forever, which you can't do. That's why we use this little symbol to represent the exact value of that number. Let's try another one of these. All right, so here we have an airplane traveling 120 kilometers per hour in a direction of 319 from Chicago at the end of this time, so end of 2 hours. How far north of Chicago is the plane? It's also west, so let's answer both questions. So here, we're going 319 again from the North Pole around to there. And our goal then, since we've flown for 2 hours at 120 kilometers per hour, after 2 hours we've flown along this diagonal, we've flown 240 kilometers. And the question is how far north, and it doesn't say how far west, but of course, let's get both. So why don't you guys work on that one and see if you can get it. Based on the one we just did. Sounds great. Everyone get the reference angle? What's the reference angle? What would the reference angle be if our flight path is at 319 degrees? So our reference angle is the 319 minus the 270, so 49 degrees. That's going to be the angle right in here, 49 degrees from there to there. So in our reference triangle, we're going to have a 49-degree angle here. We don't need the other one, but you could get it if you wanted 41 degrees. You don't need it, though. So eventually, you're going to have to find sine and cosine of 49. Are you going to be able to find that exactly using a unit circle or using a technique that we've used so far in this class? No. Have to use a calculator because that angle is not 30, 45, or a multiple. So definitely have to use a calculator. Yeah? Say that a little bit louder, so the 49 degrees. So we're counting from the positive north, and each quadrant is 90. So there's 90. There's 90 more, so this would be 180. There's 90 more, which takes us to 270. So if we're going from the north, that'll bring us to 270 right here. And then we've got to go 49 degrees more into quadrant 2. So we still call that quadrant 2, even though we got to it in a very strange way. We went from the North Pole around, but still quadrant 2. So if we want to solve for n and w in this triangle here, again, big picture, it's a right triangle, and we're given 3 pieces of information. There's 3 pieces we don't have, but we really only want 2 of them. We don't care about this angle. Could find it easily, though. 90 minus 49 is 41. So taking if we want to solve for w first, we're asking ourselves, what trig function involves 49 degrees, 240, and the w? What trig function would be grabbing those 3? Cosine. So cosine 49 will be w over 240. So w will be 240 cosine 49. Now, again, that 49, it's not a multiple of 30 or 45, so we can't use one of the unit circles that we talked about last time. So we have to type in our calculator. And it doesn't tell us what to round this to. The convention that we've used in this class, if we're given one side rounded to the nearest kilometer, let's round them all to the nearest kilometer. Now my math lab in the answer box might say, hey, round to the nearest tenth. If it does, you would. But for us, when we're looking at this triangle, we don't have any other information, so we're going to round it to the nearest kilometer. And what do we get when we type that into our calculator to the nearest kilometer? Say again? 157. 157 kilometers. Thank you. Does everybody agree with that? Yes. This thing is dangerous. And then the trig function that will incorporate 49, n, and 240 sine, we're opposite the 49. We're not next to it. We're not dealing with adjacent. We're opposite it. So it's going to be the sine function. Sine 49 degrees will be n divided by 240. And there we multiply both sides by 240. So n will be 240 times the sine of 49 degrees. And to the nearest kilometer we get 180. Everyone agree? 181. Thank you. 181. And the way we labeled these variables is pretty obvious. If I call it n, that's the north of the airport, and that's the west of the airport. So the trigonometric work here with the right triangle, I don't think that's super complicated. The big new thing is that bearing is coming from the north, and we're going clockwise. So that's a little just different. Say again?
I have a question. So
Sure.
on the other one, where we used the circle and the values from that, can we just plug it in the calculator the other way too?
Yeah, that would also work, and
We wouldn't get an exact function.
we would get an approximate answer. So that's the big question: is if our goal is to get an exact answer, then we don't want to type in our calculator. Although the sine function value at 30 is 1/2, so that would actually give us an exact answer anyway, because 1/2 is, not an irrational number.
Like a cosine.
But the cosine, because that's square root of 3/2, he does give us an irrational.
So what would be the exact answer for north?
This for north.
Yeah.
The exact answer. This would be the exact answer right there. Yeah, we don't have, for 49 degrees, we don't have a nice abbreviated irrational number like square root of 3 or square root of 2.
Right.
Sine of 49 is irrational, and it doesn't have an equivalent square root representation. So in a case like this, our hands are tied, and we would have to approximate. Yeah, good question.
Well, I was going to say, did the question just ask for north?
It did just ask for north. Yeah, yeah. I'll ask you for both. It seems silly not to do
Yeah.
both when,
Yeah.
we're trying to solve a triangle. Those are the two important directions when you're talking about a plane. Okay, now we know how far west. Let's also figure out how far north. Figure out both. Yeah. I'll ask you for both for sure. All right, let's go do a little bit more work with the reference angles. And I want to focus on some circles and looking at those and just trying to get a little more comfortable with it. So this says find the reference angle and the exact value for the following expressions. So one thing that we saw last time is that we can have multiples of 30 or multiples of 45. And when we're talking about when we're looking at these angles and we're trying to think about a circle to draw for them, typically we want to say to ourselves first, is it a multiple of 30, is it a multiple of 45, and then we'll just focus on drawing the right circle for it. And 180 degrees, or minus 180, we actually don't even need an 8. We could use an 8, we could use a 12, or we could even just use a 4, because 180 is a quadrantal angle. So quadrantal angle means that it's right on an axis. So 180 is how many pies?
Pi.
1 pi.
Sorry.
Right? 1 pi, half a circle. 2 pi is a full circle. Who knows why?
Because 2 pies are better than 1?
2 pies are better than 1. That's a good reason.
Or half tau.
Half a tau. Yeah. Half a tau. Let's see. So let me get down to my circles here. So here we just need, for that 181, we really just need this. So let's look at that first. So this is 58. And negative 180, so again, we're not dealing with an application. We're not dealing with bearing. We're just dealing with an angle. We say start at the positive x-axis. Counterclockwise is positive. Clockwise is negative. So negative 180 would be over here. That would be the angle that we're dealing with. So it has a terminal ray like that. And what we would do is take a look at the coordinates of the point there, which I call the terminal point, the point on the unit circle. And with the coordinates of that point are -1, 0. The radius is 1. So let's see. Let me ask a couple questions. What would sine of -180 be? Might as well put them all up there. Why just restrict ourselves to 1? Let's put them all up there. So for -180, and we haven't seen a lot of quadrantal angle problems, so I think it's helpful to do them all right now. So sine of 180, what would that be? 0. So here is 0. Everyone, does anyone disagree with sine of -180 being 0? Good. No disagreement. That means you all agree. 100%. Crystal clear. So we can think about the terminal ray approach. Terminal ray approach says that it's the y coordinate for sine. Right, so sine is associated with y, cosine is associated with x. Alphabetical order, x and c, y and s. Divided by the radius, and if we're on a unit circle, the radius is always 1. So it's actually just the coordinate that is sine, the coordinate that is cosine on a unit circle, because division by 1 doesn't change anything. So we get 0. And for cosine, we get -1. Tangent, 0. Y divided by x, 0. It's also thought of as the slope of that terminal ray, and a horizontal line has slope 0. And then we reciprocate. What's cosecant then? Undefined, right? Reciprocal of 0 is undefined. Reciprocal of -1 is -1. Reciprocal of 0 is undefined. So for -180, we have all that stuff. Let's go to 60. So 1050. So find the reference angle and the exact value for the following expression. So let's figure out where 1050 is. So it's certainly, is 1050, is it a multiple of 35 or 35? Is it a multiple of 30 or 45? 30? So let's go with a 12-sector circle. 12-sector circles, multiples of 30. And we have to just start counting. So 360 is 1 revolution. So here we go. Let's try to count. See if we can do it. So there's 360. There's 720. 720. What's that right there? Is that where I stop? Is it 1080 a triple? 1080 is 3 times all the way around. 1080 is a triple. And so we're going to go 30 degrees less than 3 full revolutions. So we're going to be right there. So we're at that terminal point on the unit circle, 12-sector unit circle. And the coordinates of that point on the unit circle would be, what would the coordinates of that point be? So the reference angle is 30 degrees. Reference angle is always an acute angle, so the reference angle is 30. And if we look at the coordinates of that point on the unit circle at 30 degrees, we get what? Square root of 3 over 2. And then -1/2. So with the 12-sector circle, multiples of 30, the longer coordinate is always the root 3 over 2, and the shorter coordinate is 1/2. And then we have, so that's the 30-degree piece. It's a root 3 over 2, it's a 1/2. The longer one's root 3 over 2, the shorter one's 1/2. Then we have to use our logic to figure out whether it's a positive or a negative, depending on the quadrant that it's in. So all 8 of these intermediate points on the 12-sector unit circle have coordinates that are root 3 over 2 and 1/2, and then we have to put a plus or a minus depending on the quadrant. Since we're in quadrant 4, the x-coordinate is positive, the y-coordinate is negative. And the question here was sine. Let's go ahead and just do them all since it's helpful to do them all. And the angle was 1050. And what is sine of 1050? Sine of 1050 is -1/2. Exactly. Is that mysterious to anyone? Anyone not quite sure how we're getting that? So the sine value is associated with the y-coordinate. And the radius here is 1, so if you're thinking about terminal ray stuff, you would say, oh, isn't it y divided by r? Yeah, it's y divided by r, but r is 1. So if we're on a unit circle, we're really just looking at the value of the coordinate itself. So sine will be that coordinate, -1/2. Cosine will be that coordinate, √3/2. So cosine and sine. And then tangent. That might be right. It feels a little off, though. When we divide here, the 2's go away, so we get -1/√3, so -√3/3. -√3/3. Do you see that? Yeah. So it's the slope of the terminal ray. It's y divided by x. Definitely negative. Positive and a negative, so definitely negative. The 2's cancel. We get 1/√3 for the numerical part. And then rationalize by multiplying top and bottom by √3. And flipping these over, we get -2. We get 2/√3. So this one, if we rationalize it, here we get 2√3/3. And here, when we flip it over, we would get -√3. Flip over the left fraction here is the one that makes more sense to flip over, so then we don't have to rationalize the denominator. All right, here's another one. Let's not do all of them for all of these. I think we've done, but we'll do singletons. All right, so -450. Multiple of 30, multiple of 45. What do you think? Both, maybe? -450? Both? Also a multiple of 90. It's multiple of 90. The multiple of 90, that means it's going to be a quadrantal angle. It means the terminal ray is on an axis, which actually means we could get away with just using a 4-sector circle if it's a multiple of 90. We don't really need to go to an 8 or a 12. So -450, there's -360, and 360 plus 90 is 450, so if we go the clockwise direction, this will be -450 degrees. And the point on the terminal ray here is 0, -1. And it's a unit circle, so the radius is 1. So sine of that will be equal to, whoops, can I just undo it and have it go back right where I want it? So what is sine then? So sine is -1. It's the y-coordinate there. Everyone okay with that? So we find our location on the unit circle. The sine value is the y-coordinate. The cosine value is the x-coordinate. We're on a unit circle. Tan of 480. Multiple of 30, multiple of 45, multiple of 90. What's that one? Multiple of 30, right? Good. So if we look at that, let's find 480. And it's positive, so we are rotating counterclockwise. There's 360. And then 360 plus 90 is 450, and then 30 more. So that would be 480. We can think of it as 360 plus 120. 360 plus 120 is 480. When you're doing these, it becomes very clear why you like having the 45 multiples separate from the 30 multiples. If you have one of those unit circles like this, where it's all together, it's really easy to get messed up when you're saying, oh wait, that's only 15 degrees, 2 of them is 30, but then one of these is 30. Very easy to get tangled up, so I definitely recommend keep them separate. multiples of 30, multiples of 45, then every single sector is the same, and you just have to count. A lot easier. So, coordinates of that point on the 12-sector unit circle, let's identify which coordinate's longer than the other. So the reference triangle is right there. Which coordinate's longer? The y value is going to be bigger in magnitude than the x value. So the leg is longer for the y coordinate. So that's where the root 3 over 2 goes. So the x will be negative 1/2, and the root 3 over 2 goes in the y position. So the longer leg is root 3 over 2, the shorter leg is 1/2, because root 3 over 2 is bigger than 1/2. Root 3 over 2 is bigger than 1/2. 100% on that? The square root of 3 is bigger than 1. If they have the same denominator, you can just compare the numerators. So root 3 over 2 is the longer one always. 1/2 is the shorter one always. All right, now this is asking for tangent. So for tangent, we have to do y over x, and that's minus root 3. Y over x. The 2's cancel. Root 3 over 2 divided by 1/2 is the same thing as root 3 over 2 times 2 over 1. And root 3 over 2 times 2 over 1 divided by 1/2. That's the same as root 3 over 2 times 2 over 1. The 2's cancel and you get root 3. And in this case, minus root 3 because there's a negative sign. All right, 315. Definitely not a multiple of 30. So we're hoping 45. We're assuming 45. And if you think for a couple minutes, you probably say, oh, yeah, definitely 45. So 315 is 45 less than 360. So we're going to go, there's 270, 3/4 of the way. 270 plus 45 is 315. So that will be 315 degrees. On the unit circle, radius is 1, and the coordinates of this point are root 2 over 2 and negative root 2 over 2. So the nice thing about the 8 sector is that both coordinates have magnitude root 2 over 2, and you just have to put the pluses and the minuses in the right place, which you can do easily based on the quadrant. So secant of 315 then, we have to remember that that's the reciprocal of which one, sine or cosine? Cosine. So this is 1 over cosine of 315. Cosine 315. So we have to look over here. Cosine's the first coordinate, and if we flip that over, we are going to get square root of 2 once we simplify it.
I just want to clarify. How do we get root 2 over 2 again for both? Root 2 and negative root 2?
So when we're looking at the reference triangle here, the reference triangle here is a 45, 45, 90 triangle. Right? 45, 45, 90 triangle. And we can force, so the typical way when we started was we said 1, 1, square root of 2 for the 45, 45, 90. But if we want to force that triangle to fit into a circle of radius 1, what do we divide all three sides by? Square root of 2, because we want to force the hypotenuse to be 1 to fit into a unit circle. So if we divide all three sides by square root of 2, we get that. So that forces these coordinates right there to be 1 over root 2 comma 1 over root 2. And 1 over root 2 is the same as root 2 over 2 if we rationalize the denominator. So it's coming, all of our coordinates are going to come from those representative triangles, the 45, 45, 90 and the 30, 60, 90. And the key difference is that to squeeze it into a unit circle, you have to force the hypotenuse to be 1, so you divide by whatever that hypotenuse is. And that will give you the x and y's. All right, sine of 135, multiple of 45, and negative. So we're rotating from the positive x this direction, and that'll be right there. It'll be 3 sectors of 45 in the clockwise direction. 45 plus 45 is 90. 90 plus 45 is 135. And in the quadrant, in quadrant 3, on the 45, on the 8-sector circle, multiples of 45, we have root 2 over 2 for both coordinates and magnitude, but we're in quadrant 3, so they both should be negative. Because we're in quadrant 3. And so then what is sine of negative 135? Minus root 2 over 2? And it's this one, not that one. It's the second coordinate. Sine is second. Yeah?
So would root 2 over 2 and root 2 over 2 always be true if you're dealing with 45
Any multiple of 45 will always be root 2 over 2. Yeah. And then you have to decide. It could be positive or it could be negative, depending on the quadrant.
Okay.
Multiples of 45. And when I say multiples of 45, I'm being a little sloppy, because when I say multiples of 45 or always have a root 2 over 2, I mean more technically multiples of 45 that are not also multiples of 90 that are putting you on a quadrantal angle. So we're talking about the multiples of 45 that put you on one of those 4 intermediate points. So there's 45, there's 135, there's 225, and then 315. Yeah. So it's got to be on one of those intermediate points. All right. So let's take a look at one of these. I talked last time about inverse trig functions, and we talked about how they will work if you're looking for an acute angle. But you're not always looking for an acute angle. So what we're going to do here is look at a couple of situations where we need to use a reference angle because the inverse trig function is going to give you something that's not accurate. So let's first look here at tangent. Tangent of theta, 0.260. The first thing I want you to be thinking of when you see that, when you see the function tangent, and you're thinking about tangent values, my preference would be that you start thinking about the slope of a terminal ray. We've seen that the value of tangent is the slope of a terminal ray. Or line, you can think of it as a line through the origin. So when I see that, I'm thinking about a line with slope that's about a quarter, about 0.25. So when we go to draw this, it's got to have a slope of a quarter. But the other key factor here is that there's 2 places. Right, if we drew this line right here, right, that line has slope roughly 0.25, roughly 1/4. There's 2 places. There could be quadrant 1 or quadrant 3. So we need a little more information, and they've given us that information. They say, hey, but we're in quadrant 3. So we're thinking about a terminal ray like that. The slope of that is about positive 0.25. It's about 1/4, so we're saying it's going to be equal to 0.2460. We look at our terminal point right there, and the question is, what is theta right there? All right, so if we're hoping for the best, we're thinking, oh, don't I just type in inverse tangent of 0.2460? And we get this 13.82 degrees, if we round to the nearest hundredth. Obviously, that angle is not 13.82 degrees. It's more than 180 degrees. Right? So it's not as simple as just typing in the inverse trig function of the ratio to get the angle, if the angle is not acute. If the angle is acute, it's between 0 and 90, always works. But if the angle is not between 0 and 90, Here, we absolutely have to use a reference angle. There is some other geometry that you could use, but the most straightforward way that I can give you a procedure for is if you use a reference angle. And the reference angle is going to be, I'm going to put a little hat. This book uses a prime, not a hat. Some books use a hat, some books use a prime. Theta prime is going to be called the reference angle. And the way we are going to find theta prime is by doing the inverse trig function of the absolute value of the ratio. This ratio was positive, so it didn't matter. That's going to be the reference angle. So that's what I say over here. To find the reference angle, take the inverse trig function of the absolute value of the right-hand side. That'll give you your indicator of how to figure out theta from theta prime. So the reference angle is the inverse trig function of the absolute value of the other side. And so what do you think we do with that reference angle? We're in quadrant 3. So last time, or maybe it was the time before, we talked about how you find an angle from a reference angle. It was last time. Quadrant 3, what do we do to a reference angle? Add 180. If we're in quadrant 3, we've gone 180 plus the reference angle. By definition, the reference angle is acute, and the reference angle always is between the terminal ray and the x-axis. So in quadrant 3, that's the reference angle. And that angle gets added to 180 to find theta. And therefore, and it didn't tell us what to round to. I'll just leave it to the nearest hundredth. We'll do whatever they tell us to do. So that would be our angle theta. We take the 180, we add the reference angle. Right. Let's try one that's in quadrant 2. So this second one, I have secant of theta is equal to a negative number. And they give us, and right away you say, oh, well, there's two places. Secant and cosine are reciprocals of each other. So if secant is negative, cosine is negative. Cosine is the x-coordinate on the unit circle. And there's two places where the x-coordinate is negative. X's are negative in quadrants 2 and 3. So we have two choices. They narrow it down for us. They say, hey, take the choice in quadrant 2 between 90 and 180. All right. So first off, we're going to do a reciprocal here. Our calculators don't have all of the inverse trig functions. They just have most of them, just have the 3 primaries. So we would do the reciprocal here. And like I say up there, the reference angle, which this book represents with a theta and a prime, a little prime. Some books will put a hat over the theta. This book uses a prime. Theta prime will be the inverse cosine of the absolute value of the other side. So that's going to be the reference angle. So we type that into our calculator. Make sure you wrap it up. So I'm going to type inverse cosine. It puts the left parenthesis. And then 1 divided by, and I want to do absolute value, so I just don't put in the minus. 1.0485. Wrap it by closing the parentheses. And we get 17.5 degrees. If we round to the nearest tenth. Let's just go to the nearest tenth. Okay. All right. So we are in quadrant 2. All right, they tell us quadrant 2. So let's just draw some terminal ray in quadrant 2. Let's put our terminal point there. This is a unit circle. And that angle, that reference angle, lives right between the terminal ray and the x-axis. So in quadrant 2, the reference angle sits right there. That angle right there is our 17.5 degree angle. The question, though, says find theta. Theta is the angle that starts at the positive x and rotates into quadrant 2. So how do we find theta? minus, right. So it's going to be 180 minus the reference angle. Exactly. So we subtract off and we get 162.5 degrees. That will be our theta. Make sense? All right. Now this is actually, and we will see later why. Yeah, go for it.
How do we get 17.5 degrees?
By typing in inverse cosine of this.
And that's just wrapped in parentheses, right?
Yep, so it's 1 in the numerator divided by, and it's absolute value, so we take off the minus sign and just put 1.045. 1.0485 in the denominator.
Because I did that and I got 1.62. I mean 162.5.
You left the minus sign in there.
Oh, okay. That's fine.
Yeah. But now, this is interesting. This happens to be one that actually would work if you just typed inverse cosine with the negative in there. It doesn't always work, but with cosine it does, and we'll see why in a couple of weeks. But the habit you want to get into, if you're trying to find an angle, using a reference angle, take the absolute value of this side, get the reference angle, and do it this way. If you do that, it always works. It's hard, to, especially at this point, to remember, oh, if it's cosine and it's in quadrant 2, it actually will work. But if it's cosine in quadrant 3, it doesn't work. If it's sine and it's in quadrant 4, it does work. You know, that's hard. So it's much easier if you're trying to find theta at this point. Find the reference angle, inverse trig, absolute value, acute angle, and then geometrically decide whether you add or subtract. All right, let's do one more down here. What time is it? Yeah, let's do. Actually, which one do I want to do? I feel like we've done. I think we've done enough of these. If we have time at the end, I'll come back and do another one. But I feel like you get the hang of it. And if you have trouble, we'll definitely do more. But I want to make sure that we have enough time to do the graphing, because we have a lot of graphing to do today. So let's focus there. Okay. So we've kind of, what I've tried to lead up to this moment before this conclusion is that when we're thinking about our unit circles, it's really just terminal ray stuff. It's what we did last time. So we're going to try to summarize now the unit circles based on what we just sort of saw building up to what we were just doing, where I was saying, oh, the terminal ray point is on the unit circle, the radius is 1. So we're just going to summarize that now. So what we've seen is that we typically start with our representative 45, 45, 90 triangle. If we want to force that to live in the unit circle, we're trying to force that hypotenuse to be 1. And to force that hypotenuse to be 1, we divided all three sides by root 2 over 2. Excuse me, by root 2, giving us coordinates root 2 over 2 and root 2 over 2. Okay, so this is just summarizing what we've kind of been noticing all morning. And this will be going forward, instead of sort of thinking about the terminal ray and saying, okay, terminal ray with a radius of 1, we're really just going to try to zero in on the coordinates and not worry about the radius anymore, because the radius isn't going to matter because it's 1 on the unit circle. So once we've generated the root 2 over 2 for the x and the y coordinates, then we're purely using symmetry. To get over here, we have the same type of reference triangle. Right, there's the reference triangle right there. So 45, 45, 90, we just have to put the minuses in where they need to go, the d minus. Reference triangle down here, right there. Negative root 2 over 2, negative root 2 over 2. And again, radius is 1. Okay, so from here on out, instead of thinking about a terminal ray with a radius of 1, we're really just going to think about the unit circle values. This is cosine right there, and that is sine all the way around for any angle. And similarly, for the 12-sector circle, we We're going to stop thinking about the terminal ray if we have a multiple of 30 and just think about the unit circle. And we said that our representative triangle for a 30, 60, 90 was that. And if we want to force that to fit right here where the radius is 1, what do we divide all three sides by? 2. That will force our representative triangle to fit. So these points right here are root 3 over 2, 1/2. Here, 1/2 root 3 over 2. And let me just try to point out, without making too much of a mess here, move that 1. I've got to move it even further. There. All right, so is it, as I was talking earlier about short sides and long sides, is it clear that there's 30, 60, 90, if we pick any one of those 8 intermediate points, so picking that point, there's a short leg and a long leg. And if it doesn't matter which one you pick, if we come over here into this quadrant, we would have there and there. There's a short leg and a long leg. So for each of those 8 intermediate points, there's going to be a short leg and a long leg. The short leg's always going to be the 1/2. The long leg's always going to be the root 3 over 2. And then we have to put in the pluses and minuses. So we come over here. What's the x value for this point? Negative. Root 3 over 2, because the long leg is the x, the short leg is the y. If we come over here, this would be 1/2 minus root 3 over 2. Because here the x is short and the y is long. And the y is negative and the x is positive. And so the trig function values for multiples of 30 and 45 are going to become really just an application of the 2 unit circles and knowing the coordinates. You now know the exact trig function values for any multiple of 30 and any multiple of 45. Over here, minus root 3 over 2, positive 1/2. Here, minus 1/2, positive root 3 over 2. Down here, negative 1/2, negative root 3 over 2. Is there any point that you're not sure about, or how we got to root 3 over 2? Is that clear? So we took our representative triangle, divided it by the hypotenuse. And when we do that, everyone's comfortable with why that works. If you take a triangle and you scale it smaller, scale it bigger, it's similar, which means the angles are all the same. All right. So there it is. Done. Typed neatly. We'll answer these 2, and then we'll take a break. Okay. Negative 5 pi over 4. Are we rotating clockwise or counterclockwise? Clockwise, because it's negative. And we're going to skip count on the pi over, these are all sectors of pi over 4. 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. It takes us right there. So sine of negative 5 pi over 4 is what?
Root 2 over 2. Negative.
It is what? Root 2 over 2. Positive root 2 over 2, because sine is second coordinate. Sine is the second coordinate, so it's always cosine, comma, sine. So it's positive root 2 over 2. Cosine, negative root 2 over 2. It's always the first coordinate. Tangent, negative 1. It's the slope of the terminal ray. Slope of the terminal ray, it's y divided by x, negative 1. All right. How about cosecant negative 5 pi over 4? we have to reciprocate that,
2 root 2 over 2. Which is just root 2.
which ends up being root 2, right? Ends up simplifying to just root 2. Yeah. So both of those, one is positive, one is negative. This is negative 1. Okay, now you guys write down those ones from this circle. Negative 7 pi over 6. Find negative 7 pi over 6, and then write down those 6 trig values. See if you can do it. I think you can. It might take a little bit. Yeah, right. So negative 7 pi over 6. So draw the circle. Draw the 12 sector. It always helps. Anytime you're trying to evaluate an angle, if you draw the circle so you know exactly where you're at. Yeah, so where's negative 7 pi over 6 there? So if it's negative, we're going to go this direction. Yeah, it's going to be right there. So we're counting by pi over 6. So 6 pi over 6 will take us to the horizontal. 7 pi over 6 will take us there. What would the coordinates that would be? So it's the same as 5 pi over 6. Yep, same coordinates as 5 pi over 6. So which coordinate is longer? Is it x or y longer than that? Yeah, so x is longer. So that means that x is going to have the root 3 over 2, and y is going to have the half. So right now the coordinates of x has the root 3 over 2. Y has the half. Which one is that? Positive 2, negative. Positive. Yes. You're getting there? Is it making sense that the x is longer for the 7 pi over 6? You have to count over to that spot. X is negative 1 over 2. Square root of 2. And y is 1/2. So show me where would you be on that circle that's negative 7 pi over 6. So negative means we're going to rotate counterclockwise. Clockwise, this way. So we're starting right there. Negative 7 pi over 6. Each one of these is pi over 6, so we have to go 7. So what terminal point do we get? Right, exactly. Yep, that's where we are. So highlight that point. And which coordinate is the sign and which coordinate is the sign? Yep. If sine is this one, so it's alphabetic. The first one will always be cosine, the second one 1/2 sine. So sine is half. And sine is. That makes sense. So then, yeah. Is yours got it? Oh, yes, it's not. That's 8 seconds. But that's not going to help us. Oh, no, why? Oh, no. Uh-oh. Oh, that's right. Hopefully you're observing some So, sign it goes, yeah, got it. Okay. Making sense? Know where we're at in the circle? Know where we're at in the circle? Yep. You know what the coordinates are? What's that say? Oh, that's the other one. Okay.
No, it doesn't. It's only to help you. Right, but if you're ever like,
But it can help you because it can replace your voice test. No, I think we did the final is going to replace the final is in place. Yeah, if you did that.
Do the same for that one.
That would be yeah, but it can help you though.
Got it?
If you did,
Yep, yep. That's the location. And yeah, once you're on the unit circle, just find where you are and then pull out the coordinates. You just have to remember, cosine is first and sine is second. Got it? Two. Because yours goes alive and well? Okay. No.
if we were going.
So a couple things. First, let's look at, so it's sine of negative 7, 5, or 6. So you have the right point here. So we get 1, 2, 3, 4, 5, 6, 7. And so how do you get
Okay, so you just got your signs.
the y coordinate? No, the radius is 1. So when we have these coordinates, the radius is always 1. That's why we call these unit circle. So the radius is 1. But now also we have another.
Oh, yeah, so,
One half side of 2. Okay, you start with if you were in, like if you think about half, if you take like half
To
of
get
cup,
to
and
the
divide
square
it
root out
out
of
to
the
the bottom of the cup.
you're gonna time
So, but this is exactly your sign down here. That's the beauty of being on the unit circle. You're on a unit circle. You don't have to do any division. This is sine right there, and this is cosine right there. Radius is always 1 on the unit circle. So our sine doesn't change.
business.
Cosine is just that. We don't do any division.
if we're
That
ready
is
to
cosine.
also,
All right, so let me just summarize this, then we'll take a 10-minute break. First off, when we count clockwise here because it's negative, and we just count 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, right there. And you'll start to get fast. If you go half a circle, that's 6 pi over 6. Then you have to go 1 pi over 6 more. So you'll get better at counting. Don't worry. It'll come. So that will be our negative 7 pi over 6. And these coordinates that we've generated today are for a unit circle. So that means the radius is 1. And so last week we would have said, with the terminal rate approach, we would have said sine is 1/2 divided by 1. Right? But the whole point of putting them on the unit circle is that we don't have to do that division anymore. Right? If we put it on the unit circle, we've already done the division. And so all we have to do is identify the coordinates. So that coordinate right there is sine. We don't no more division to do. And this other coordinate is cosine. Automatically. So once we find our location, then we find the coordinates. And again, notice on the 12-sector circle, there's always going to be one leg longer than the other. The longer leg has root 3 over 2 tied to it. The shorter leg has 1/2 tied to it. And then we have to put the plus or the minus depending on the quadrant. And so when we come down to fill in our table here, sine of negative 7 pi over 6, right there, come out to the coordinate, 1/2. No more division. We're good. Cosine negative 7 pi over 6 is the first coordinate. Tangent. It's sine over cosine, or y over x. The 2's cancel, so we get 1 over root 3 negative. So negative 1 over root 3. Rationalize that denominator, and we get negative root 3 over 3. And then we flip them over to get these guys. So this is 2 over root 3, and if we rationalize that, we'll get negative 2 root 3 over 3. Flip this one over, and we get negative root 3. So those will be the trig function values for negative 7, 5, or 6. All right, let's take a 10-minute break. If you have a question on any of this, if you're feeling disoriented, come and talk to me during the break, and we'll figure out some strategy. Tangent values, what I've done here is just sort of drawn a summary of the tangent values for the 8 and 12 sector circle, and I've mentioned it several times that the value of the tangent is equal to the slope of the terminal ray. So if we look at 45 degrees here, the slope of that ray, the slope of that line is 1, value of tangent is 1. Come over here, value of tangent is negative 1, and that slope is negative 1. So the tangent value always matches the slope of the terminal ray. So that gives you a nice kind of check on things. And one thing to keep in mind is that in quadrant 2 and 4, slopes are negative, so the values of your tangent should be negative in 2 and 4. 3 and 1, positive. Right? Those are lines of positive slope. 12 sector. Same idea. Horizontal line, slope is 0. And then we have our 2 here, undefined slope there. So let's look at the 2. What I want you to just make a note of, and I'll mention it quite a bit throughout the semester, it's going to get convenient. It will be convenient if you make the following observation. This terminal ray at 60 degrees is steeper than that terminal ray at 30 degrees. If you look at the slopes, this one is a third that one. This one is a third as steep. It's this slope divided by 3, so it's less steep. Right? And so we'll see that a lot during the semester. I'll talk about the 12-sector circle, and we'll be looking at a terminal ray that's one of those intermediates, and I'll say, is it the steeper one or the less steep one? And if we sort of identify that and look and remember, or at least be able to calculate fairly quickly, that the steep terminal ray has slope root 3, the less steep one has slope root 3 over 3. Those will be helpful touch points as we go through the semester. Okay. All right. We're moving towards graphing. Graphing. Lots of graphing to come. We're going to approach it in a fairly systematic way so that you can get your graphs. But there is a lot that goes on with trig function graphs. It's not like parabolas and absolute value functions where it's kind of straightforward. You can't just plot points with trig functions. It gets too crazy. Okay, you have to plot some points though. So preliminary observations, what we've kind of learned up to now is that if we force ourselves to focus on a circle of radius 1, a unit circle, what we have seen now through lots of experimentation is that we can think of the coordinates of this point on the unit circle as cosine comma sine of whatever angle got us to that terminal ray. You may have rotated around multiple times clockwise or counterclockwise, doesn't matter. If you end up with that terminal ray right there and that terminal point, the coordinates of that terminal point on the unit circle, cosine comma sine of the angle. All right. So a couple of observations before we move forward. So, how do the sine and cosine values change as alpha changes? What are the sine values for alpha starting at 0, ending at pi over 2? All right, so let's try to do this visually. So we're focusing on the sine of alpha. Sine is the y coordinate, and it says start at 0 and end at 2 pi. So if we're here at 0 degrees or 0 radians, what's the y value right there? 0. Right? The y value is 0. The point right there, the terminal point, is 1, 0. So the y value is 0. So starting at 0 radians, we have a y value of 0 at 0 radians. And then as we start moving up and around, the y value is going to increase. So if we get to 30 degrees, the y value is 1/2. If we get up to 45 degrees, the y value is √2/2. If we get up to 60 degrees, the y value is √3/2. And when we get all the way up to 90 degrees, pi/2 radians, the y value is 1. So it goes up to 1. So in quadrant 1, the y values go from 0 to 1. Then we go to quadrant 2. We're up here at 1. And then what happens to these y coordinates as we start rotating through? Yeah, they go down to 0. The y values start to shrink from 1 down to 0. So they go to 1 to 0. And then in quadrant 3, the y values start to become negative. Y values there are 0, and they're going to go all the way down to -1. And then quadrant 4, they're going to go from -1 back up to 0. Does everybody see how that works? So what we're going to do, our goal, is to graph the sine function as a function of the angle. So the angle, in this case I've written it as alpha, but whenever we graph functions, we always let x represent the independent variable and y represent the dependent variable. So what we're going to do is convert, and we're going to talk about the sine of x. I'm not going to write that in a unit circle, though, because that gets really confusing if I write sine of x right there for this y piece. So when we graph the functions, we won't be labeling the unit circles with x's and y's for that, but because that gets a little too confusing. So when we graph y equals sine x, x is representing the angle. So that will be 0, pi/4, pi/2, 3 pi/4, pi, all the way around. And the y values are going to have this pattern. Y values are going to start at 0, go up to 1, go down to 0, go down to -1, and back up to 0. How about the cosine values? Let's look at quadrant 1 here for a minute. The cosine values are going to go from, let's see, what's the cosine value over there at 0 degrees? 1, right? Cosine value is 1 out there. It's the x value. And then as we start to rotate through quadrant 1 as alpha or theta or whatever you think of your angle as being, as we rotate up to pi/2, your x value is going from 1 to 0. Up here at pi/2, the cosine value is 0. The x value is 0 on the top of the unit circle. So our cosine values are going to go from 1 to 0 in quadrant 1. And then in quadrant 2, let's see, x value is 0 there. And as we rotate around, what's the x value there? -1. So we're going to go from 0 down to -1. And then in quadrant 3, x value there is -1. And we're going to go to there where the x value is 0. So we're going to climb back up from -1 back up to 0. And then in quadrant 4, we're starting down here, x value is 0, and then we end up over here where the x value is 1. So we're going to go from 0 up to 1. And so when we graph y equals sine x, y equals cosine x, what we're doing is just targeting the x values or the y values on the unit circle. And we're going to draw a picture of how those values change as the angle changes. So the angle is the independent variable, which typically we've thought of the angle as theta or alpha or some Greek letter. But now we're going to talk about the angle as x. So we're going to look at the angle being x, and then the y coordinates are going to be either the y coordinates for y equals sine of x will be these guys. The y coordinates for cosine of x will be these guys. So we're going to look at how the sine and cosine values change as the angle changes. So here we go. Here's the sine function. So the sine function, we just went through these values here. So on the x-axis is now an axis of angles. The x-axis is an axis of angles. The y values here match the y coordinates on the unit circle because sine grabbed the y coordinates. When we look at cosine, The y values here correspond to the x coordinates on the unit circle, because cosine picked the x coordinate of the unit circle. So let's look at sine first. So at pi over 2, so here, if you look at all these y values, that's what we just wrote down on the previous slide. The y value here at 0 degrees is 0, or 0 radians. The y value jumps up to 1, goes down to 0, goes down to -1, goes back up to 0, goes up to +1. And you can see that this pattern right here, this is going to be called the first period of sine. The first period will go from 0 to 2 pi, and then it repeats itself, and then it repeats itself. Both directions. We're going to get this curve that repeats itself. Trig functions are called periodic because they repeat themselves every period. As one period ends, then a new one starts. So the period of the sine function is 2 pi because that's how long it takes before it starts to repeat again. Every 2 pi, it repeats itself. How about the domain of that function? All real numbers. It's going to go from negative infinity to positive infinity. Right? There's no gaps. There's nowhere that this curve is missing. Right? The curve is there forever. So there's no x values that are taken out like you might do if there was an asymptote. So we can write all reals like that, or you can write it as negative in interval notation, negative infinity to positive infinity. How about the range? So range is a subset of the y-axis, domain subset of x-axis, range subset of y-axis, but we read it from the bottom to the top. So the range, the least range value would be down here, -1, and the greatest range value would be up there at +1. So it's going to go negative 1 to 1. And we put the bracket. Bracket includes. Parenthesis excludes. Bracket includes. So we put the square bracket because that includes the -1 and it includes the 1. All right. The cosine function is going to be similar. The x-axis will be angles. The y values will be the x coordinates on the unit circle. So if we look at the x coordinates on the unit circle, those correspond to the y values of this graph. At an angle of 0 radians, the x coordinate is 1. So that's why we're up here at 1. At pi over 2 radians, the x value is 0. That's why we're here at 0. The y value here is 0. At pi radians, the x value is -1, which is why the y value here is -1. So this is a picture of how all of the x values on the unit circle change as the angle changes. Okay? And that can be a little weird because now the y values are the x values from the unit circle, so that gets a little confusing. You know what I'm saying? If we look back at the unit circle here, we said that the cosine values, which are the x values of the unit circle, the cosine values or the x values on the unit circle went from 1 to 0, 0 to -1. So when we look here, the y values for this function started up here at 1 and then went all the way down to -1. And you can think of this as quadrants if you want. If it helps, there's quadrant 1. There's quadrant 2, there's quadrant 3, and there's quadrant 4. So in quadrant 1, the cosine values went from 1 down to 0 in quadrant 1. If you think about quadrant 1, the cosine value here is 1, and as we slide up to pi over 2, the cosine value there is 0. So the x-coordinate started at 1 and ended at 0 in quadrant 1. And then in quadrant 2, the x values went from 0 to -1, and then -1 to 0, and then 0 to 1. So quadrants, connect those as quadrants. Period is the same. This period is 2 pi. The cosine function repeats itself every 2 pi radians. If you're thinking about a unit circle, as you go around the unit circle, that's 2 pi, and then the cosine values start over. Right? Every 2 pi, every revolution of the unit circle, you'll get your values to repeat. Tangent. Oh, I didn't finish that off. What's the domain of cosine? Same, right? All reals? Right? There's nothing left out. There's no x value on this graph that has a y value that's undefined. Y value is defined for all x's. How about the range? Same, -1 to 1. Including, so we use brackets. Tangent function. Here, the tangent function. Tangent of 0 radians or 0 degrees. We just did that slide with all the terminal rays and the slopes. Right? Tangent of 0 is 0 because the terminal ray has slope 0. And then as we move towards pi over 2, so the slope of this terminal ray, it's getting larger and larger, right? Slope is 1 right there, slope is 2, slope is 3, slope is 4, slope is 5. And as this gets closer and closer to vertical, that slope gets more and more, it grows without bound. Right? It gets larger and larger. But at pi over 2, slope is undefined. So slope is undefined at pi over 2, and that's why we see these asymptotes. These asymptotes right here are from pi over 2, and negative pi over 2 is down here. The same type of thing happens. Here the slope is 0. There the slope is -1, and then -2, and then -10, and then -1,000, and -100,000. And it goes larger and larger in magnitude. It grows larger and larger in magnitude. But then right when we're at pi over 2, it's undefined. Right? Vertical lines have undefined slope. And so that's what these asymptotes represent. And of course, they repeat themselves. And we notice that the domain of this function is smaller than the last two. The domain is pi. Right? From negative pi over 2 to pi over 2, that's pi radians. And then it repeats itself. So it takes negative pi to pi for one period. Next pi repeats itself. Next pi repeats itself. So here we have a period of pi. Domain, not quite as simple as the other two. Because domain is the set of x's for which the function is defined. And at an asymptote, the function is not defined. So when we look at that, the domain is all real numbers except x is not allowed to be an asymptote. We have to take away all these x values that don't have y values. Right? So all those asymptotes, those are where an x value has no y value. The function is undefined. So we have to take away those x's. There's an infinite number of them. So we better come up with a shortcut, because we don't want to list them all out. That would take a while. So what we notice is that, oh, hey, these asymptotes, they're all pi radians apart, right? So what we can do is set up a counter. And we could say, OK, all right, x can't be equal to pi over 2. That's the first non-negative asymptote, which is usually how books will do it. They'll start with this one. They'll call that the first asymptote right there. The first asymptote that's greater than or equal to 0 is where they'll start. All right, so there's the first one. And then we're going to set up this counter. Plus, they're pi radians apart. So if I did pi over 2 plus pi, I would be right there. Pi over 2 plus pi would be there. Pi over 2 minus pi would be there. And so we have to put a counter on here. And does this book call it K or N? K. Some books call it K, some books call it N. I taught out of books for years that called it N. All right, so pi K. So this right here gets at every single asymptote if you let K be an integer. So K is an integer. And you don't need to write this down every time. We're going to assume from here on out that if you write a K, it means it's an integer. So This asymptote right here is when k is 0. What is the k value for this asymptote? 3 pi over 2. 1. What is the k value for this asymptote? 2. So the k's are going to count off all these asymptotes right here. How about the k value for this asymptote over here? -1. And mathematically it works. If we do pi, if we look at k equals -1, pi over 2 minus pi, pi over 2, if you subtract off pi, you get to minus pi over 2. So that will be our systematic way to count off the asymptotes. Does everybody agree when you look at that, that that's going to take away every asymptote? So we start at the first non-negative one. We figure out how far apart they are, and then we throw on an integer counter. So we're just going to step them off one by one. Okay. Range. Oh, rails. Right, we project our function onto the y-axis. There's no y values that are excluded. There's no real number that is not the y value for some angle when you take tangent of that angle. All right. Now the hard ones. The reciprocal functions. So we're going to look at the basic 6 functions. When we say a basic trig function, we mean there's no shifting, there's no stretching, there's no reflecting. So when we talk about the basic 6, we're talking about, you know, just bare bones. Y equals sine x, y equals cosine x, y equals cosecant x. Bare bones. No transformations. We'll do transformations very soon. Okay, cosecant. So cosecant and secant, we will graph using a guide principle. We're going to use a guide function to graph these two. And looking at this picture, it's probably pretty obvious that the guide function that we use for cosecant is sine of x, because that's the reciprocal of cosecant. For secant x, our guide function is going to be cosine x. It's only these two functions that we're going to use a guide for. We will not use a guide for cotangent. We won't use a guide for tangent. We won't use a guide for sine or cosine. So only secant and cosecant. These are the only two that we're going to use a guide for. And we use the reciprocal function. So the reciprocal of cosecant is sine, so that will guide us. And if we look at the first period of sine, that's right there, first period, 0 to 2 pi. Sine values from 0 to 2 pi, we know how they go, right? They start at 0, they go up to 1, they go down to 0, down to -1, back up to 0. So those are the sine values. Cosecant is the reciprocal of sine. So let's take a look. Right here, let's look at these points right there first. What is the value of sine for all three of those? 0. The value of sine is 0 for 0, pi, and 2 pi. And when you take the reciprocal of 0, you get undefined. So to graph cosecant, the first thing we do is graph our three asymptotes. Because wherever sine is 0, cosecant's undefined. Now let's focus on these points. Let's focus on that, those 2 points. What is the value of sine at pi over 2? 1. What is the reciprocal of 1? 1. So sine and cosecant will share a y value there. And now let's go to 3 pi over 2. What is the value of sine at 3 pi over 2? -1 at 3 pi over 2. The reciprocal of -1 is -1. So sine and cosecant will share a y value at 3 pi over 2. Okay, now the interesting part. So we've got those kind of parameters on the outside. Now let's look in here. The value of sine starts at 0 and it climbs up to 1. So all of these values in here that are not those two, the green dot or the purple dot, all those x values, all those y values here, so for an angle between 0 and pi over 2, all these y values here are between 0 and 1. So we can think of them as proper fractions if we want. They're really fractions, right? They're below 1 and above 0, so they're really fractional in nature. And what happens when you take the reciprocal of, say, 1/2? What do you get? 2. When you take the reciprocal of 1/10, 10. Reciprocal of 1/100th, 100, right? So all these guys in here are less than 1, so when you flip them over, when you take their reciprocal, the corresponding values on cosecant are going to be greater than 1. And the closer your sine value gets to 0, say 1/1,000,000th, so really close to 0, that y value, really close to 0, when you flip it over, you get 1,000,000, which is way up there. So you're growing without any bound. It's growing forever as you get closer and closer to 0 for the angle. All right, so that's why we have those asymptotes. That's what it looks like. We've got a curve that opens up, a curve that opens down, and then they repeat themselves. So the part that I'm highlighting in green here, this is the first period of cosecant. That's the first period. So you've got those two curves, an up curve, a down curve. They are not parabolas. Do parabolas have asymptotes? Right? Parabolas go out forever. Forever. Right? They keep stretching wider and wider and wider and wider. These guys do not do that. They are constrained by those asymptotes. So they do not stretch out forever and ever. They just go up. They are functions, though, so they're climbing and they're not on top of them. You know, a function, it has to pass a vertical line test. So this curve does not come back on top of itself, but it doesn't go out this way. It's constrained by that asymptote. Okay, so not parabolas, even though they look very parabolic. They're not parabolas. How about the period? So this repeats itself every 2 pi. Yep, same as its guide. The domain, all reals but the asymptotes. So the typical procedure to count off all these asymptotes is to take the first non-negative asymptote. So the first asymptote that's greater than or equal to 0. So this has an asymptote right at 0. So we'll consider that our first asymptote. And how far apart are these asymptotes? So the domain is 2 pi. So half of 2 pi is pi. So yeah, they're every pi radians. Asymptote every pi radian. Every pi radians, there's an asymptote. And that just keeps happening. So x cannot be equal to the first non-negative one. Let me just write it in there, even though we don't need to, is 0. And then we figure out how far apart they are. And then we throw on our counter. So 0 plus pi k. Clearly, you don't need to put the 0 if you don't want. So the 0, when k is 0, we'll get our first asymptote. That will be k equals 0. This will be when k is equal to 1. This will be when k is equal to 2, etc. How about the range? You read from bottom to top for range. You push onto the y-axis. So that range is going to start way down at negative infinity. It's coming up. Stops at negative 1. Do we include or exclude the negative 1? Include it, so we put a bracket. Then there's some values here that aren't in the range. There's a gap. And then they pick up again at 1. Yeah, good. And they continue on without bound. secant. The second function that we use a guide for, secant. The guide is its reciprocal, which is cosine. And cosine has this as its first period. That's the shape for the first period of cosine. And the shape for the first period of secant is this. We've got a curve that opens down, and then we have two partial curves on the top half. So the first period does not include the other parts of this upward curve here. All right. Does not include. It's only half. Period is still 2 pi. For sure. The domain, it wants to be all reals, but it can't be because we've got asymptotes, so we've got to take away the asymptotes. So the asymptotes here, let's focus on those for a minute. So these 2 points here, these 2 points there and there are where the cosine is 0. So if we reciprocate, secant will be undefined at those 2 points. That's why we have the asymptotes. And that asymptote right there, I've kind of mushed over the point there, but that's at pi over 2. And this is over here at 3 pi over 2. So how far apart are these asymptotes? Pi. So we've now looked at our basic functions. For tangent, the asymptotes are pi apart. For cosecant, the asymptotes are pi apart. For secant, the asymptotes are pi apart. What do you think for cotangent? Pi apart. Yeah. So the asymptotes for any one of our basic functions that has asymptotes, they'll be pi apart. All right. So our first non-negative asymptote is pi over 2. And then we put our space, the distance between consecutive asymptotes is pi, and then we throw on our counter. So that will be the domain for that function. And range is going to be the same as for cosecant. We start way down south, negative infinity. We get to -1, we stop, have a gap, pick up again at 1, and go up forever. So that'll be the range. When we're graphing our guide function, these 5 points will be key points in helping us graph the reciprocal function. So those 5 points will typically be called the guide. Well, they call them key points. So the 5 key points on the guide are those. They figure out where the asymptotes are. They figure out where the touch points are. And that helps a lot. Last function, cotangent. All right. First off, there's a little difference between this one and tangent. When we look at our reciprocal functions, sine and cosecant line up. They both go 0 to 2 pi. Cosine and secant both line up. They went 0 to 2 pi. Tangent went from minus pi over 2 to pi over 2. Cotangent does not follow the same suit. Right? So sine and cosecant lined up, secant and cosine lined up, but tangent and cotangent do not line up. Tangent went from, I didn't actually highlight the first period. Let me highlight that first period of tangent. Tangent's first period goes minus pi over 2 to pi over 2. But cotangent's first period goes from 0 to pi. So for cotangent, it's right there. That's the first period of cotangent. 0 to pi. Not negative pi over 2 to pi over 2. So it's got a shift. There's a shift. Asymptotes, there and there. Cotangent's undefined at 0 degrees, and it's undefined at pi degrees, or pi radians, I should say. So if we look at the unit circle, on the right, that point is 1, 0. On the left, that point's negative 1, 0. Cotangent is x divided by y. So at 180 degrees, pi radians, we have negative 1 divided by 0, undefined. And at 0 degrees, or 0 radians, we have 1 divided by 0, which is undefined. So that's where our asymptotes are. And cotangent's going to go down to the right instead of up to the right, like tangent did. Cotangent of pi over 2 is 0. Right up here, cotangent, that's 0, 1, and cotangent of an angle is the x coordinate divided by the y coordinate. So that's 0. And if we want to think about it, cotangent is positive in quadrant 1. Right? These values here, those are quadrant 1 values. These are quadrant 2 values over here. And if you think about x over y here, x over y is positive. Here, x over y is negative. So that's why we see the value of cotangent go from positive to negative as we go from 0 to pi. Period? How many radians? Pi, because it goes 0 to pi. So that will be our domain, or our period. The domain, it wants to be all reals, but we've got asymptotes, so we've got to exclude them. What's the first non-negative asymptote? Right, it's 0. The first non-negative is 0. First non-negative. So the first one that's 0 or more is 0. And then how far apart are they? Pi. So plus pi, throw on a counter. That will get all the asymptotes. And I should say x not equal. X not equal. So we have to exclude those from the real line. And then, of course, the range is all reals. Whew. Those are the 6 trig functions in their basic form. And here's where I think it's really helpful to get comfortable using Desmos. We're going to do a lot of transformations. We're going to see a lot of graphs. And Desmos is a wonderful tool to double check your work, to explore graphs. Desmos.com, click graph. And I usually click the wrench and put it in projector mode so that it's brighter and that everything's a little bigger. And then for the x's, since we're graphing trig functions, you come down here and put a step of pi over 2. That will help. And then you can just graph. So let's notice a couple of things about graphs. So sine of x is that. And another nice thing about Desmos is if you put a letter like A, B, or C in, it automatically is going to say, hey, do you want this to be a slider? Sure, make it a slider. So now it makes it AX, and I can slide on this A. A is a variable. A is going to affect the period. So we said that the basic sine function repeated itself after 2 pi radians. Now, as we move that slider, we can see, okay, if we put in a coefficient inside the angle, right there, of a number that's greater than 1, did the period increase or decrease here? Right? Decreased? It's repeating itself more frequently. Everyone agree with that? So maybe what I'll do is put the slider. You can play it. I don't want to play it. So as we increase that coefficient, we're decreasing the period. Now if we go to the other side of 1, let's get to 1. 1. So there it is, period's 2 pi. And if we go less than 1, so a fractional value, the period stretches. It increases. Yep. Now let's not worry about the negatives right now. So that's a nice little feature, though, that you can add a slider. And let's take a look at moving that coefficient to the outside. So on the inside, it affects the period. On the outside, it's going to affect what we call the amplitude. The amplitude is going to be the distance from, I'm going to call this line right here the center line for the graph. And the amplitude is going to be the maximum distance that we are from the center line of the graph. So the amplitude in this case is going to be 5.4 because the max point is 5.4 above the center and the low point is 5.4 below. So that's going to be the amplitude. Amplitude is always going to be a positive number. It's measuring that maximum distance, the maximum variation away from the center line of the graph. That will be our amplitude. And of course, if we put that A on the outside, what kind of shift is that going to be? If we add it. Whoops, took away the wrong letter. Right? Shift. That kind of stuff. So this program is just really cool. It's so easy to use. And if we want to put in sine of 2x, do that, and shift it. So a great way to check your work. If there's going to be lots of graphing by hand. On the exam, you're going to have to graph by hand. But this is a super way. You can always check that you've made the right graph by going to Desmos and looking. Very, very convenient. So let's take a look at the next slide. Time to be creative. So what I want to do is the next section. These two sections should be merged in some sense. So in section 6.5, the one we just finished, they have just the basic graphs, but they don't modify them at all. And there's a couple of things I want to do now that will lead us into 6.6 that we'll focus on just sine and cosine for a minute. We'll sort of talk about some ways you can graph a function. Because the big key is that you want to graph a transformed sine or cosine. The chances of your period being 2 pi and your amplitude being 1 are really small. Right? So we want to be able to understand how to do that. So let's look at a few examples here. So let's talk about the details of how things work, and we'll focus just on sine. Sine is the easiest function because it starts at the origin, and it does this nice little loopy thing, and the asymptotes are on the edges. It seems to be the easiest one. The asymptotes, the zeros are right on the edges. So let's take a look at the following function, and let's analyze how we would compute the graph of this. So I want to make that not a 2 though, because I want a 2 on the inside. 2 on the inside is going to actually help us a little bit. Let's put a 3 there, put a 2x, and let's put a minus pi here. I'm not going to worry about putting an up-down shift at the end right now. That's the easiest one to understand. So let's just take a look at this. We have 5 properties that we're going to look at for every trig function. And I'll write them down in this order every single time. R, A, P, P, S, V, S. So I'll write those 5 properties down every single time we look at a function. Every time. And I write them in this order because we can pull them off as we go across the function from left to right. So we're going to start out in front. And a lot of this should be reviewed because you did transformations in college algebra of algebraic functions. So a lot of this is the same. So a reflection. Do you think this has a reflection or not? Yes, I hear yes. And that's familiar from algebra. And the key is that the leading minus. That tells us that we're going to flip everything through the x-axis, right? So we have a vertical reflection. We're going to reflect vertically through the x-axis. So yes, there's a reflection. The next thing in our property list is the amplitude. So the amplitude is going to be dictated. We saw already when we played around with Desmos this leading coefficient there is going to indicate the amplitude. The amplitude, though, is positive. It's always a maximum distance. So what we do is take the absolute value of the leading coefficient. That will give us the so-called amplitude. Now, period. When we played with Desmos, we saw that this coefficient right here adjusted the period. So this is our period adjuster in here. So that guy is what's going to change the period. The basic period we said was 2 pi. And what we saw was that if we put a number there bigger than 1, we took the period and we contracted it. And so, and if college algebra, it depends on the class you took. You may or may not have done horizontal stretches and contractions. I don't know. You may or may not have done them. In college algebra, and I'm saying this true here, if the coefficient on the inside is larger than 1, it's going to be a horizontal compression. If it's less than 1, it's going to be a horizontal, what do we call it? Stretch. Horizontal stretch. You may or may not have done that. It's not that big a deal. For us, we're very precise. What we say is this. The period is going to be the basic period for sine. So that numerator is because that's the basic period for sine. And then we divide it by the leading coefficient. So this 2 right there, that is this denominator down here. So that tells us exactly how that coefficient is going to adjust our period. And so our summary here is that the period of our transformation is pi. So it will do 2 complete cycles within 2 pi. So sine does 1 cycle in 2 pi, but sine of 2 pi, or excuse me, sine of 2x will do 2 of those within the 0 to 2 pi interval. All right, now here's a tricky piece. The horizontal shift, and I don't know, it depends on how your teacher in college algebra taught you. The way I'm going to teach you here is to factor. Before you can see the horizontal shift, which in trig we call it the phase shift, you need to factor out the leading coefficient of the angle. So if you don't factor, you'll have your phase shift. The chances of getting your phase shift right are smaller. So if you factor, do you agree that that's the right factorization? You take the 2, you distribute it. 2 times x is 2x. 2 times pi over 2 is pi. Right? What do you think the phase shift is then? With a minus x minus pi over 2 in there. Phase shift would be, phase shift is the same as horizontal shift. To the right?
Pi over 2?
Yeah, exactly. Right? To the right, pi over 2. So it's always the opposite of what we see. We see a minus pi over 2. Horizontal shift will be opposite. And in this case, vertical shift's on the outside. I didn't put anything there, so it's 0. So that phase shift thing, that horizontal shift, everybody's probably uncomfortable with that. It's one of those things that, let's take a look at a parabola for a minute. Let's just get rid of this trig function stuff, and let's look at y equals x squared for a minute. So there's y equals x squared. And the question always is, why am I shifting to the right when it's negative? Why am I shifting to the left when it's positive? And it's actually very easy to see if you graph the following. If you come in here, and you, not up there, down here, if it lets me over there, minus, let's put an a in there, slider. There's a way I can make that an integer if I want. Let's do that. I think that will do it. So now, yeah, okay. Okay, so we're at 0. And I want that square to be on the outside, of course. So there's our parabola. You learned about the vertex of a parabola, HK. Right? That's what you studied that a lot. And let's just look at some values. If we put in a 2 there, I better take away that. There we go. So then we're at 2. So when it's minus 2, we're over here at 2 because 2 is the number that gives us the vertex. It gives us a 0 for the function value. If we have x minus 2 squared, if we plug in x equals 2, that's where we get 0. That's where we get the vertex. So when we put a minus 2 in here, we've actually moved the vertex so that it's 2 that makes us 0, makes the function value 0. So if it's x minus 5 or something, then we have to plug in a 5 for x to get the y value of 0. So it's always just going to be opposite of what you see because you're shifting in a way that changes the vertex. So x minus 5 is shifting the vertex over to 5, 0. And it's the same with the trig functions. Same exact thing with the trig functions. So that's all that's happening. Same thing. So the phase shift is that. Now, how do we graph this darn thing? Okay, so we draw our coordinate system. That's how we're going to start. And we're going to go through it step by step. It's actually pretty straightforward if we follow all these steps carefully. So there's one thing that I'll always identify, and that's the shape. The shape for sine looks like that, and there are 5 key points on sine, which are right there. So that is the shape for sine. We'll always have that shape. Be stretched or something might be done to it, but that's the shape. And here is our procedure. The first thing we do is go to the phase shift. This is step 1 for the graph. Phase shift, I'm going to put that as pi over 2, right there. That is going to be the left edge of that first period. So the phase shift, right, it took it and shifted it. So that's where we're going to start. Instead of starting at 0, we'll start at pi over 2. How far away is the right edge of this graph? If the left edge is at pi over 2, how do I get to the right edge? What do we add to the phase shift? We add the period, right? So the phase shift tells us where to start. The period tells us how far we need to go to complete one cycle of the graph. So that right endpoint over here is going to be at pi over 2. Let's see, there's pi. There's 3 pi over 2 if I'm adding by pi over 2s. That will be the period. We take the phase shift, add the period to it, and that will give us our interval where the graph is going to live. That interval is pi units long, which is what the period is. Okay, so that was second step, looking at the period. Third step, we're going to look at the amplitude. How far above and below the center line do we need to go? 3. So I'm going to go up 3 and down 3 from the center line. The center line is right there. And technically, this actually is step 4 because step 3, this is 0 here, so it didn't do anything. If there's a vertical shift, we're going to shift the center line up or down. So technically, step 4 tells us how far to go above and below the center line. We'll focus on that next time. And then a reflection. Okay, so that's going to be the last thing. So here we go. We're almost there. Key points. There are the key points listed over here. 3 on the center line. So 3 key points right on the center line. Typically, these 2 non-center line points are up and down like that. But what's true about the reflection? Flip them. So these are going to go down to the amplitude and up to the amplitude. And there is our graph. It goes on forever in both directions. But we're only interested in the first period. I will ask you on the test for the first period. If you want to sort of indicate that it goes on forever, you can put little arrows. That's fine. But I'll just ask you for the first period. And that's it. My brain hurts too. Yeah. It'll get easier as we go. We'll do lots of these next week. But yeah, we'll stop there. Look at that. See if it makes sense. Really come through it this weekend because graphing is going to come fast and you're going to need practice. You got to get your hands dirty. Study group tomorrow. What time is the study group tomorrow?
12 to 1.
Oh, 12 to 1. Where?
In the Student Org Center.
The what?
The Student Organization Center.
Oh, is that on the B level? Oh, it's upstairs. Coffee. Right here.
Coffee. Get your coffee and then we'll graph.
Coffee and graph.
What a fun Friday afternoon.
Oh my gosh. Killing it with graphing on Fridays. All right, I will see you all next